In this video, we'll be going over find minimum in rotated sorted array. So suppose an array of length n is sorted in ascending order is rotated between 1 and n times. For example, the array numbers 0 to 7 might become 4, 5, 6, 7, 0, 1, 2, which is rotated 4 times, or it can be rotated 7 times to get the original array back. So given the sorted rotated array nums of unique elements, return the minimum element of this array. So in our first example, we're given this array 3, 4, 5, 1, and 2. So we can see that is sorted in ascending order. So it's 1, 2, 3, 4, 5. But then it's rotated 3 times to get this array. And then our minimum elements is 1. So we return 1. Let's go over the thought process. So let's first go over the brute force approach. The brute force approach is to iterate. We can iterate through the input array once to find the minimum elements. Now, this approach will cause us O of n time complexity because we visit each element once. Now, let's implement a more optimized approach. Now, when searching for an element inside a sorted array, the most optimal way is to use binary search. Now, the input array currently is rotated and sorted. So it's sorted and then rotated. Now, how can we implement a modified binary search for this problem? Now, for example, if we currently have the mid elements, or the elements at the middle, we can compare the mid elements with the current leftmost elements, which we will call left. So if mid is greater than or equal to left, we know that the left side must be sorted in ascending order. Must be sorted. Now let's call the rightmost elements right. Now if mid is less than or equal to right, this means the smallest elements must be located on the left side with mid inclusive. Now what if mid is greater than right? This means the smallest elements must be on the right side instead. Now what if the mid element is currently less than the elements on the left side? So for example, we have a 2 here, and then we have elements on the right side, on the left side, 3, which is greater. If it's greater, this means the pivot position, or the point of rotation, must be on the left side. This means the minimum elements must be on the left side, so we will continue to search leftward. So if mid is less than left, this means the pivot point must be on the left side, so the smallest elements must also be on the left side. So we will continue our search leftward with mid inclusive. Now let's go over the code. So we're going to create 2 variables. Left is our current left boundary, initially 0. And then we have right, our current right boundary, initially the last index, so nums.length minus 1. Now while left is less than right, we're going to perform our binary search here, or our modified binary search. We're going to calculate the mid index. So mid is equal to left plus right minus left divided by 2. Now if nums mid is less than or equal to nums left, this means the left side is sorted in ascending order. Now if nums mid is less than or equal to nums right, this means our current boundaries is sorted in ascending order. So the smallest element must be located on the left side. So we're going to search leftward with mid inclusive. So set right to mid. Now else, this means nums mid is greater than nums right. This means the smallest element must be on the right side instead, so I'm going to set left to mid plus 1. We are going to search rightward. Now else, this means nums mid is greater than nums left. Actually wait, if nums mid is greater than or equal to, it's greater than or equal to, if it's greater than or equal to nums left, this means the left side sorted. And then if nums mid is less than or equal to nums right, yes, then this will be fine. We'll continue to search leftward. Okay. So if nums mid is less than nums left, this means the pivot point must be located on the left side. So I'm going to set. So we are going to search leftward with mid inclusive. So I'm going to set right to mid. Then we can return nums left, which is our minimum elements. Now let's go over the time and space complexity. With time complexity is log of n, where n is the length of the input array. So we visit each element once. No, we perform binary search. And our space complexity is of 1. Let's go over the code. So we're going to create 2 variables to keep track of a current boundary. While left is less than or equal to right, we calculate the mid index. If nums mid is greater than or equal to nums left, this means the left side is sorted in ascending order. So if nums mid is less than or equal to nums right, this means we can search leftward with mid inclusive. Else, the minimum element must be on the right side instead, so we're going to search to the right. Else, if nums mid is less than nums left, the pivot position must be on the left side. So our smallest element will also be on the left side. So we're going to search to the left with mid inclusive. Then we can return nums left, the smallest elements. Oh. Let me know if any questions in the comment section below.